with asymptotes, not asymptotes, x and y intercepts, which are these things that we're learning about right now. And it looks like this, so let's get rid of this. So x and y intercepts, I think the easiest way to remember what they are is this picture. This is a nice picture definition of the x and the y intercepts. You have some graph. The y-intercept is where it touches the y-axis. And the x-intercepts are where it touches the x-axis. OK, so that's a nice picture definition. If you also remember what a graph is, right? What is a graph? Well, the height of the graph above some x value is the value of the function. So if you remember that from last time, then you can translate this picture of x and y intercepts into what they mean. So the y-intercept here is the height of the function at x equals 0. This is the height at x equals 0. And the height at x equals 0 is exactly f of 0. This is the height at x equals 0, which is exactly y equals f of 0. So that's that height. So the y-intercept is exactly f of 0. That's the y-intercept. What about the x-intercepts? Well, the x-intercepts are the places where the height is 0. So the x-intercepts are the places, I'm going to say locations, and locations. And by locations, I mean x values, right? The x values where f of x equals 0. So if the height is 0 at these locations, then f of x equals 0 at those locations. So we're looking for the places where f of x equals 0. Those are the x-intercepts. And the y-intercept is simply f of 0. Basically, I've just done a re-derivation of this picture of what is written on the next slide as procedure 2. To find the y-intercept, you just plug in f of 0. The y-intercept is 0, y0. To find the x-intercept, you solve 0 equals f of x0 for points x0. So let's see, were you guys able to do it for this function? Let's see what people said. So the y-intercept, people said, okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 420. This guy's getting ready for the weekend. Negative 2. Negative 2. 855 people said negative 2. Negative 2 is correct. Oh, actually, I take it back. This person was just saying what time the class, the class started at 4:20. That's when I got here. OK. Negative 2. The y-intercept is negative 2. That is correct. That is correct. So if you said negative 2, good job. So again, all you got to do, f of 0 is 0 squared minus 0 minus 2. That's negative 2. This is the y-intercept. Okay, and very technically speaking, that is the y value of the y-intercept. So if somebody asks you for the coordinates of the y-intercept, they're how far across? 0, negative 2. So just watch out, this point, right? The height is y equals f of 0. Technically, this point is 0, f of 0. So if somebody asks you for the point, just watch out for that. Okay, that's that one. Can I do the reveal back, go back to the other mode? Okay, great. What about the x-intercepts? What did people say for that? Negative 1, quite popular. 2, 1, some people said 1. Ah, 1, okay, good. 1 is an instructive wrong answer because the correct answer is negative 1. What's the other one? The other one is 2. Did people also say negative 2? Oh, no. Interesting. Okay, so the correct answers are negative 1 and 2. Why are the correct answers negative 1 and 2? Again, we are solving for the x-intercepts. We solve f of x equals 0. And f of x equals 0 in this case is x squared minus x minus 2 equals 0. So it's a quadratic equation. You could use the quadratic formula like we did last class and in that extra video I posted to solve what it is. Or you could factor it. And factoring it is easier because I told you as a hint how to factor it. So the factoring is x plus 1 times x minus 2 equals 0. So we're talking about the product of two numbers, x plus 1 times x minus 2. You multiply two numbers together to get 0. Well, the only way that can happen is one of the two numbers has to be 0. So x plus 1 equals 0, or x minus 2 equals 0. And x plus 1 equals 0 is the same thing as x equals minus 1. And x minus 2 equals 0 is the same thing as x equals 2. So the answers are minus 1 and 2. If you said 1, just watch out for that. X plus 1 equals 0, the minus 1 moves to the other side. That's why you get a negative sign there. So the answers are minus 1 and 2, which again, I think most people got. So congratulations to those who got it. That's, I think, all we're going to say about x and y intercepts for now. Straightforward concept. It's used all the time. Yeah, x and y intercepts matter because we're talking about where the function is 0 or the height at 0. If you're talking about like a business or something, you're like, when does it have 0 money? You know, that's important. Like, when is our profit 0? Like, we care about that a lot. That's why people care about x and y intercepts. Okay, let's move on to the next thing, which is asymptotes. Asymptotes. So in this section, we're doing the non-technical version. So it says here in non-technical terms, today we're doing the picture version, the picture version of asymptotes. And I will warn you that later on in the course, we're going to do a more algebraic, like more exactly correct version of asymptotes. So this is like kind of the warm-up for more asymptotes. So what does asymptote mean? The asymptote of a function, they are the straight lines that the graph of the function gets arbitrarily close to. This is the super secret keyword for this section, arbitrarily close to. What does arbitrarily close mean? It means no matter how close you can get, it gets that close. So you want it to be within 0.1, it gets within 0.1. You want it to be within 0.0001, it gets within 0.0001. You want it to be within 0.00000001, it gets that close too. This is very similar to what we talked about in the first class with 0.99 repeating. So 0.99 repeating, it got arbitrarily close to 1. That is why it was 1. An asymptote is the same idea. The function, so the function f of x is getting arbitrarily close to some line. That line is called the asymptote. Okay, so we're going to consider 3 types of asymptotes. And actually, I'm going to make a correction here. We're only going to consider 2. We're going to consider 2. There's horizontal asymptotes. Those are horizontal lines that the function gets close to. So it's a horizontal line. The function is getting really close to a horizontal line. There's vertical asymptotes. That's a vertical line, and the function is getting really close to a vertical line. And there's another type that we're not going to do in this course. So we're going to cross this one out. This one is banished from the course. I'm choosing to banish this one from the course. Banished. So we're not going to do slant asymptotes. They're a little bit tricky, and I think vertical and horizontal asymptotes are already tricky enough. So let's see an example. And by the way, yeah, this is what it says later. Later on, we're going to do limits, and limits are the formal version of asymptotes. Today, we're just doing the picture version. So here's an example. Here's the function f of x equals 1 over x minus 1 plus 2. That's shown here. That's these black lines. And there are 2 dotted lines. There's a vertical dotted line that looks like this at x equals 1. And there is a horizontal line at y equals 2, rather. Y equals 2. That's a horizontal line. And those are the asymptotes. So x equals 1 is the vertical asymptote. Y equals 2 is the horizontal asymptote for this function. If you can see the picture, you can start to see this function is sort of like hugging these 2 asymptotes. So we want to explain, using the picture, why it is true that x equals 1 and y equals 2 are the asymptotes. So we're going to fill in the blanks here. At x equals 1, the function is blank. Thus, the vertical asymptote is given by x equals 1. So x equals 1 is going to be the answer. In the blank there, we have the reason why x equals 1 is an asymptote. And I want to, before I put in the right answer, I want to tell you a really common misconception that is the wrong answer, the wrong thing to put in the box. So this is the thing that people say that is not right. They say at x equals 1, the function is undefined. Undefined. Right? This function, it is true that it is undefined. If at x equals 1, we are dividing by x minus 1, we have 1 over x minus 1, it is true that the function is undefined there. But it is wrong to put the word undefined in this box. The statement, the function is undefined, thus the vertical asymptote is x equals 1, is a bad statement. That is not true. Some functions that are undefined have a vertical asymptote. Some functions that are undefined don't have a vertical asymptote. So the fact that the function is undefined here does not help you figure out if there's an asymptote. And I'll give you an example. Let's draw in pink here. Let me draw another function. I'm going to draw another function which is undefined at x equals 1, but no vertical asymptote. I'm going to draw that in pink. Let's call that g of x. Here's my g of x. Are you guys ready? It goes like this. It's undefined at x equals 1, and it just has a hole, and then it goes like that. So this function is undefined at x equals 1, but it has no vertical asymptotes. So it's very careful you understand this distinction between undefined and a vertical asymptote. A vertical asymptote is, it's related sort of to undefined, but it's not the same thing. So be careful on that. So what is the correct answer? The correct thing you should put in the box, the correct thing, is the function. Okay, let's look at the picture and try to describe in words what it's doing that makes it a vertical asymptote. A vertical asymptote is when the function gets really, really close to the dotted blue line. So you could kind of see that the way it's getting really, really close is sort of up here and down here. It's as the y values get very, very large, the graph of the function gets really, really close to x equals 1. So at the top, it's kind of getting shrunk in there, and at the bottom here, it's getting shrunk in there. And this is really happening because the function is blowing up, right? The function gets vertically so high, it goes all the way up to sort of plus infinity in some sense over here. So plus infinity in quotes, right? Because infinity is not a number. And over here, it's minus infinity. It's going so far down that that is the sort of reason why it's getting close to the blue line. So the fact that it's a vertical asymptote is because the function is doing the stretching out thing, and by stretching out all the way up to plus and minus infinity, it can get really close to the dotted blue line. So the correct answer, one possible correct answer, is the word blows up. It blows up. This is like very informal, obviously. The function blows up, and thus the vertical asymptote is x equals 1. This is super informal, but I think this is capturing what's going on. The function is blowing up, and that's why it can get really close to the blue line. By moving all the way up to plus infinity, it can hug this blue line arbitrarily close, and that's why it has a vertical asymptote. So that's how I would describe it to somebody if I was just chatting. I would say the function blows up at x equals 1. If you want to be more formal, the formal word for blows up is unbounded. 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 So if you want to put in a fancy word and you don't want to say blows up, then you can put in unbounded. Unbounded means it doesn't have a bound. If it doesn't have a bound, then it has to blow up, right? That's why blowing up and unbounded mean the same thing. I'll tell you guys a funny story about a mathematician who was on a plane ride in the US, when the TSA was created to crack down on plane terrorists and so on. And this mathematician was talking about unbounded things to his other mathematician friend, and they were working on Cartesian coordinates, like we saw last class. So they had Cartesian coordinates, points in the plane, and they were talking about unbounded things. And one of them said to the other one, I'm blowing up points on the plane. And the TSA did not like that, and he got arrested, and he had to explain blowing up just means unbounded. Points on the plane, I don't mean a plane in the air. I mean the Cartesian plane, and it was a big mess to sort out. So that's one reason to avoid the word blows up, because it means something else as well in real life. But in math, it means unbounded. Okay, so now you know all about vertical asymptotes. I think vertical asymptotes are the trickier one. What about horizontal asymptotes? That's this green line, y equals 2. This one's more simple. As x tends to plus or minus infinity, so very large values of x, over here and over here, if you look at really large values of x, f of x, the height of this function, gets closer and closer to 2. The height here is getting really close to the height 2. This distance is tiny. Thus, the horizontal asymptote is y equals 2. So that one's not as complicated. Okay. So horizontal and vertical asymptotes, that's what we're going to be doing in this course. The next page over here, if it'll let me go to it. The next page over here, we're skipping this one. So this one is another banished one. This is a slant asymptote. So we're going to skip this one. Banished. Are there any questions about horizontal or vertical asymptotes? Okay, if you guys are so good, tell me the horizontal and vertical asymptotes for this function. I will just let you think about it for a minute. Horizontal and vertical asymptotes for this function, f of x is 1 plus sine of x over x. There's the graph. Look at the graph, figure it out. And then I'll open up a Math1030 with the question in a second, but just try to answer the question. What are the vertical asymptotes and horizontal asymptotes? Okay, so you've had a second to think about it. I'm going to open up a Math1030. Before we open up the Math1030, you probably realize there are no vertical asymptotes. So that's not too bad. No vertical asymptotes. Why are there no vertical asymptotes? Well, the function is not blowing up anywhere, right? The function doesn't go to infinity anywhere. It's a perfectly reasonable function between 2 and 0. Never does anything super crazy. No vertical asymptotes. So the only question is, what are the horizontal asymptotes? Well, we're only looking at positive x values here. Nothing can happen as x goes to minus infinity. So the only potential thing is what happens for very large x values. And essentially, you guys should be split into two camps. There's one camp that believes x equals 1 is an asymptote, is a horizontal asymptote. And there's another camp that says x equals 1 is not a horizontal asymptote. So some people think this picture, it does count as an asymptote, and some people don't. And it really comes down to the issue of does crossing count or not? So the next question is, does crossing count or not? True or false? It is possible for the function to cross a horizontal asymptote. So if you select true for this one, it means that you think it is a horizontal asymptote. And if you select false for this one, you think that this is not a horizontal asymptote. So tell me what you think in terms of true and false. It really is the same question as, do you think x equals, I wrote x equals 1, but I meant to write y equals 1. Y equals 1 is either is or is not. If y equals 1 is, then you are a true person. And if y equals 1 is not, you are a false person for this question. Okay, and I'll give you 1 minute to tell me what you think. Okay, let's see what you guys said. Let's see what you said. True or false? Okay, it's a 66 to 38 split, so very close to 50-50. Does that add up to, were you able to select more than one? Okay, maybe I didn't set the settings right. Obviously, it can't be both. So 66% of people think it's true. Only 38 people think it's false. Majority on true. You know, you can see it both ways. Here's why people think it's true. It's true because we are getting closer and closer to y equals 1. This is the argument for true. True because this is why. Why could it be true? Why could the answer be true? Could it be true? True because the function gets close to y equals 1. It's getting close to y equals 1. And what does close mean? Well, close just means within a certain distance. Sometimes it's a little bit above, like here it's like 1.0. Oh boy. Yeah, that's my other countdown timer. Okay. Okay, so here it's like 1.01, like a little bit over 1. And over here it's like a little bit under 1. It's like 0.99. So it's sometimes a little bit above, sometimes a little below, sometimes exactly equal. But in any case, if you look at large enough x values, it's getting closer and closer. And that closer and closer, that arbitrarily close, is what defines a vertical asymptote. So that is why the answer could be true. Why could the answer be false? Why do people choose false? Why could it be false? So does anyone have a good reason of why it could be false? I know of exactly one reason that is very compelling on why a lot of people, like 40% of people, choose false. Did you have your hand up? No? Okay. Yeah. Yeah, so the function touches the asymptote. Why is that not allowed? So the function, I agree the function touches the line y equals 1, but we need a reason. Why does touching it mean it's not an asymptote? Do you have a good reason? No. There's one great reason. There's one reason everybody tells me whenever this comes up. Yeah. Is it equal to 0? Okay, so it's true. If the function was like undefined or something tricky, then I think there would be some ambiguity, right? Like if the function had gaps and it wasn't defined, but this function is defined everywhere, right? This function makes sense for all x values. So that would be a good reason. If it's not defined, that's a great reason. The reason people always tell me that they choose false is because my high school teacher said so. Because my high school teacher said so. High school teacher said so. Okay. And this answer is wrong. So it's not false, it's true. True is correct. I don't know why a lot of high school teachers tell you touching is not allowed. Oh, maybe I do know why the touching is not allowed. The correct answer is true. It is true. So it is okay for an asymptote to touch the line. That is totally fine. The only thing that matters is if it's getting arbitrarily close. And touching is arbitrarily close, right? So another example that somebody asked about in the last class is what about the function, we did this, what about the function y equals 2? So the function y equals 2 looks something like this, right? It's just always 2. This is y equals 2. Does that function have a horizontal asymptote? Yeah, it does. It does. It's 2. Y equals 2 is a horizontal asymptote for y equals 2. That is perfectly fine. It's always touching the asymptote, but that's perfectly okay. So if you want to go back to the definition, you can add in a little star here. You can say getting arbitrarily close, and then you can say touching allowed. Touching is allowed. Is allowed. Okay. So that's one thing to watch out for. And in fact, there was a hint here. In some cases, even crosses. That's in the definition over there. And down here, there's a little footnote that says, in this example, it shows that a graph can cross its horizontal asymptote. So it is okay to cross. Okay. So the asymptote is y equals 1. In this little paragraph over here, we're going to fill in the reason why it is y equals 1, sort of algebraically. And the reason is, we're looking at the function 1 plus sine of x over x. If you just looked at sine of x, just sine of x on its own, sine of x on its own is between -1 and 1. So sine of x is a ratio of the opposite side to the hypotenuse. The hypotenuse is always longer than the opposite side, so the sine is never more than 1. It's never less than -1. So we're looking at something between -1 and 1 divided by x. If x is a really big number, like imagine x is 100,000, you have like 1 divided by 100,000. What is that? It's getting closer and closer to 0. So you have a number that's between -1 and 1 divided by a big number. The big number is x. Let's call this number x. And so y is getting closer and closer to 1 plus 0. 1 plus 0. Right? So the function is 1 plus sine of x over x. Sine of x over x is getting close to 0. So what is y getting close to? 1 plus 0, which is 1, equals 1. So the horizontal asymptote is y equals 1. Okay. This little paragraph is basically doing limits, which we're going to do later in the course, but doing it in words. Later in the course, we're going to learn limits properly with algebra and like steps and rules. This is like the warm-up with words and pictures. Okay. Any questions or comments about that example? This is like a tricky thing that some people get wrong. You guys did better than the 230 class. It was closer to 50-50 at the 230 class. You guys, it was almost 70-30. That's quite good. Okay. Anybody for questions? Okay, so the next couple of things we're going to cover here, are, okay, I want to close this. Okay. So there's two things on polynomials and on algebraic functions. And polynomials and algebraic functions, this is less of something that you're going to do a lot of problems with, but more of just like knowledge that you should know. So what is a polynomial? A polynomial is something that is made from powers of x. So sums of powers of x. And they look like this. The most important ones you should know are the constant functions. So like something like y equals 2, that's a constant function, a degree 0 polynomial. Linear functions, mx plus b, and quadratic functions, which we saw already today. So if you know these three, that's almost all the ones we'll be using in this course. You can do higher order ones like cubics, quartics, quintics. We mostly won't be doing those. Okay, so these are all polynomials. Polynomials have nice properties. You can spend your life in your PhD doing polynomials if you want. We're moving on to rational functions. Rational functions are ratios of polynomials. So things like this, ratios ratios of polynomials. These are called rational functions. The thing you got to watch out for rational functions is because we are dividing by something, you have to be careful when you try to divide by 0. So functions are not defined for the values of x that make q of x equals 0. If q of x is ever 0, then p of x over q of x makes no sense, and so the function is just not defined there. If we were going to draw it as a graph, there would either be a hole in the function or an asymptote or something. Something interesting would happen to the function at those points where q of x equals 0. Okay. So here's a little example of that. I'm just going to do it. For what values of x is the rational function f of x equal x squared plus 2x plus 3 over x plus 6 not defined? You might think, oh, I need to factor the top or something. But where it's not defined only has to do with the bottom. So the only thing that matters is x plus 6. And it is not defined when x plus 6 equals 0. That's x equals negative 6. So not defined at x equals negative 6. That's something you're going to have to watch out for constantly. Dividing by 0, no bueno. Make sure you know not defined there. All right. So now that we've done polynomials, which, like I said, you can spend your entire life studying in 5 minutes, we're going to move on to algebraic functions. What are algebraic functions? Algebraic functions are things that can be constructed from a finite number, so like 100 or 10 or 3 algebraic operations using polynomials. So if you take like 3 polynomials and you put them together with addition, subtraction, multiplication, that's an algebraic function. If you take 100 polynomials and put them together, that's still an algebraic function. And so here are some examples. Polynomials count. Rational functions count. That's the ratio of 2 polynomials. Things with radicals count, so square roots and so on. Those count because they come from polynomials like this. This comes from the polynomial y squared equals x squared plus 1. So that's a polynomial, and so you get this function with square roots and so on, you can get those too. Things like this, 1 over x squared counts, and even crazier things like this crazy guy with a cube root and dividing by a square root, those count too. So if it's made up of dividing, plusing, timesing polynomials, that's an algebraic function. Who cares? Why would I invent this thing, algebraic functions? Well, the interesting thing about algebraic functions is that not every function is algebraic. There are functions out there that are so crazy that no matter how many times you stick together polynomials and divide them and add them, you will never, ever make that function. These are called the transcendental functions. These are the transcendental functions. And these functions are so wild, you can't make them, cannot be made from polynomials. Cannot be made from polynomials. And that's the reason it's interesting to have a name for algebraic things. Like you kind of might believe that if I just know how to add and multiply and I can do it enough times, I can make any function, but the answer is no, you cannot make the transcendental functions. And you might think these transcendental functions are useless, like they must be really crazy functions, right? But the answer is that actually some basic functions we use all the time, like sine of x or e to the x or the logarithm of x, those are all transcendental functions. And that's why we need to know the difference between transcendental and algebraic, to just know these functions are going to be harder, more difficult than polynomials. Okay. The last little side note that is exciting and is a taste for the future if you keep doing math is that even though transcendental functions cannot be made from a finite number of polynomials, they can be made from an infinite number of polynomials. So just like 0.99 repeating was an infinite sum, if you do an infinite sum involving x, then you can make the transcendental functions like sine of x. So these functions are kind of have to do with infinite sums. And this kind of series, this is called a series expansion. This is used a lot in physics and engineering and stuff to get approximations. So if you keep taking math, you'll learn about these things. We're going to do a little bit of the basics. Some of it you've already seen before. Remember we said in the course earlier that the sine of x is approximately x? That's how I did really fast on the calculating sine of x. Sine of x is approximately x is the first term. So if you kind of ignore everything that comes after x, you throw that away, you just get sine of x as x. That's what we had before. Okay, that's all we want to say about algebraic and transcendental functions. It's just for you to know, so you know when someone says algebraic, what are they talking about? All right, that's it for this chapter. Are there any questions or comments about this chapter before we move on to the next chapter? Yeah. Can I scroll up a little bit? Yeah. I can scroll up a bit. You want this page or like the previous page? This page is good. Okay. Yeah, I mean, I underline things to like emphasize them. You guys should take notes however you want, right? Like, don't feel like you need to copy. Like, you know, I probably wouldn't write this one down on my notes. I'm curious. Let's do an experiment. I'm going to draw a happy face here, and we'll see at the end of the year. I'll do a check and see how many people drew the happy face in their notes. Okay. So we're going to move on to chapter 6. Chapter 5 was basic functions. What is chapter 6? Advanced functions. So we're kind of doing functions again, but more definitions, more in depth than last time. So just like before, a function is a rule or a machine that inputs one number x and outputs another number y. What's new this time is we're giving names to the possible inputs and we're giving names to the possible outputs. So the domain is going to be the possible inputs and the range is going to be the possible outputs. This is nicely written on the next page. So the domain of f is the set of input values and the range of f is the set of output values. I would also think about adding the word possible, right? Possible. The possible things you could input, the possible things you could get as an output. The domain and range are really important to know because they're like part of the operation of the function. So if you like my analogy of a function is like a factory that has inputs and outputs, the domain is what am I allowed to feed into the factory, right? Like if the factory is machines that input cotton and you input a brick, that's like a bad day. Like you're going to break your machine. That's why you need to know the domain. The range is what could possibly come out of the function. So if you're expecting a sweater, but the function can only possibly output t-shirts, then like that's good to know. That's why we need to care about the domain and the range. So we're going to use this notation df, that means the domain of f. Rf is the range of f. And we're going to use the same notation as before with f and g and so on that we've seen already. Okay. So we have the notation for domain, we have the notation for range. We talked about the graph of a function last time. Now we're going to do the graph of a function written in symbols. So the graph of a function is the set of ordered pairs, right? A graph of a function is a bunch of dots on the Cartesian plane. What is it? It's the set of all xy pairs. So set of xy pairs such that what? Such that x has to be in the domain of f, x is one of the allowed inputs, and y is exactly f of x. So x is an input, x is an input, and y equals f of x is the output at f, the output for, let's say, input f, input x. So when you feed x in, you get y, that pair xy is added to the graph. The graph is all the possible points altogether. That's what the set notation means. Okay, so in words, we plot input values against output values. It's the same idea we talked about before. It's just written in symbols to scare you away. Okay, so functions, they can be discrete or continuous or piecewise. This is talking about, is the function a graph with like a smooth curve or does it have like dots that are separated? And in fact, our first example here is the function f of x equals 2x, but x is in n. N is the natural numbers. So this is 1, 2, 3, and so on. So this is the function whose inputs are only allowed to be whole numbers, like 1, 2, 3, 4. So it's like a factory. If you try to feed in 1.5, the whole factory breaks, right? Like it cannot possibly input 1.5. It has no idea what to do. It only ever inputs whole numbers, 1, 2, 3. What does the graph of this function look like? It looks like this. Here's the graph of the function. So the graph consists of all the pairs where you have all the possible x values and the y value that goes with it. We said the possible x values, those are the domain. We said that's 1, 2, 3, 4, 5, ... And over here, look, I've listed all the possible xy pairs, 1, 2, 3, 4, and so on. Those are the x coordinates. What are the y coordinates? Well, to get them, I have to feed them through 2x. So the range of f is going to be what you get when you take 1 and feed it through the function 2x. If x equals 1, then 2x is 2. So the range is 2, 4, 6, 8, and so on. And you see those appear here, 2, 4, 6, and so on. And if you plot them as points, as xy points, you get this nice picture in the plane. So here is 1, 2, here is 2, 4, here is 3, 6. So this is the nice, and then it goes on forever, ... forever into the sky. So that's the function f of x equals 2x, but watch out because the domain is not what you expect. The domain is just the natural numbers. That's how you would specify it. Any questions or comments about this example? It's a little bit different, right? All the graphs you've seen so far in the course have been like continuous, liney things. This one has dots. That's called a discrete function. So on the next 2 pages are 2 other graphs. So here's one, and it's got 4 points, and here's one, and it has 3 points. And I want you guys to try to guess what the formula is. See if you can guess what the formula is for these 2. I'm going to open up a Mathematize where you can put in your answers. So guess the formula and tell me when you have the formula. Okay, there's like 30 seconds left. If you're struggling a bit, it is multiple choice, so just pick your best guess for examples 2 and 3 and try to figure it out that way. Okay, let's see what you guys said. What did you guys say for these 2 things? I'm going to start with example 3, this one, because that one's a little easier. Let's see, what did people say? Reveal counts. I want this one, example 3. So 22 people said x, 60 people said 1. You might think 1 is a number. How is 1 a function? Well, 1 is a perfectly valid formula for a function, right? This is the function g of x, on the next page, g of x equals 1. What does that mean? That means no matter what input you get, you always have 1 as the output. This is like the function that ignores what you inputted and always outputs 1. And that perfectly matches what's going on here, right? It's 1, 1. When the input is 1, the output is 1. When the input is 2, the output is still 1. When the input is 3, the output is 1 again. So it perfectly matches what's going on here. The output is always 1 no matter what you input. That matches what's going on. The only thing that you need, in addition to g of x equals 1 to specify this, is to say what the domain is. So the domain is the set 1, 2, 3, right? If you just said g of x equals 1, then someone might misunderstand that you mean this function that is always 1, right? Like that function, like a horizontal line. That's not what we mean. So by specifying the domain here, we have specified exactly which function we're talking about. You might also say g of x equals 1. X is one of 1, 2, or 3. X is in the set 1, 2, 3. That's another way to say it. And let me turn this off if it's going to let me. All right. Okay. So that's the function what we're talking about. It's the function that's always 1. The domain is the set 1, 2, 3. The range of this function is super easy. The range of f is just 1. That the only possible output you can get is 1. Nice and easy function. Okay. So be careful, it's not this guy. All right, let's go back up to this example. This example is trickier. I wonder what people said for this one. In this one, 71 people said not a function, and not a function is the right answer. So very good for people who said that. This one is not a function. If I were to ask you why this one is not a function, a lot of people would say because of the vertical line test. And it is true that this is not a function because of the vertical line test, but this one is so simple, you can describe why it's true without saying by the vertical line test. And if you have that description, you will understand why the vertical line test is true. So I'm going to make a little description here. Why is it not a function? Why is it not a function? And here's how the argument goes. If it was a function, then f of x, f of 2 equals something. Let's call that something y, for some y. So if it was a function, f of 2 would take on exactly one value, f of 2 would be y. But 2, 2 and 2, 4 are both in the graph. So there's a problem here because we have at x equals 2, there's 2, 2, but there is also this other annoying point, 2, 4. And so there is no way to know what is the value of y. It could be 2 or it could be 4. It's not specified by this graph. So therefore, there is no value of y that works. Therefore, there is no y that works. And if there's no value of y that works, our original thing we said, if it was a function, that must be false. So therefore, not a function. Not a function. So, and what we've described is exactly the reason the vertical line test is true. So the vertical line test, we're going to see it formally written down in a second. It says that anytime the graph touches 2 points in one vertical line, it definitely cannot be a function. Why is it true? The reason we just said. The function, if it was a function, can only have one value. If it has two values, that's a contradiction. It cannot possibly be a function. So this one is just not a function. Not a function. Okay. So down here is the vertical line test. And here is an example of a more complicated sort. This is the graph of the equation y squared equals x. And y squared equals x looks like this funny parabola. And we know for sure that y squared equals x is not a function because it fails the vertical line test. So this is a vertical line that goes through 2 points, and therefore it is not a function. It is true in this case that y squared equals x, this is not a function, but it is actually two functions. It is two functions. It's y equals plus the square root of x. Let me do these in some colors. Y equals plus the square root of x and y equals minus the square root of x. So y equals plus the square root of x is this top half, and y equals minus the square root of x is this bottom half over here. And even though y squared equals x, the whole thing is not a function, it has two halves, and each half on its own is a function. And if you put the halves together, you get the full thing. So this is something that often happens, is that any equation, even though it might not be a function, it might be made of a number of functions. So if you're into this stuff, there's a theorem called the implicit function theorem that says every equation can be cut up into a number of functions. Here you're seeing it in action with two functions. Okay, so that's the vertical line test, splitting things into two. This is essentially the most basic things you need to know about functions. We're going to do one more example today. Any questions or comments here about the vertical line test or anything else? Okay, so the last example we're going to have you do is to find the domain and range of a real function. So here's more vertical line test, right? This one is not a function. This one is a function. Vertical line test. Okay. We're going to skip this line thing. I'll do that next time. We're going to skip the circle thing. I'll do that next time. I want you guys to do this one because it's not too hard. F of x equals x squared. You guys tell me the domain and the range. And the domain and the range are both intervals, and I want you to enter them into Mathematize as intervals. So you have to enter in which bracket it is, what the first number is, what the second number is, and what the last bracket is. And you have to type in /infinity with a backslash for infinity and a -/infinity for a minus infinity if you want to have infinity in your intervals. So take a stab at that. I'll give you guys 2 minutes to do that, and then we'll take it up. Okay, so there's only like 30 seconds left. Try to get your answers in. If you need to take a guess, that's fine. Okay, I'll give you guys another. So remember, it's \infd if you want infd. In the interest of finishing on time here, you can put in 6s or 7s. Let's go with 7s. Lucky number 7. If you don't know the answer and you want to say I was here and I tried, but I don't know the answer, just put in 7s. And I'll take it up in like 1 second here. So get your answer in. Okay. So again, we're looking at this function. It looks like this. The domain is going to be the set of things on the x-axis. All the possible things on the x-axis. What is the range? Those are the possible y values. This function is always above the x-axis. The possible y values are just that, right? Everything above the x-axis. So what is the correct answer? Let me reveal, and you guys will see if you got it right. Let's reveal the answers. So it's minus infinity to infinity. How many people got this right? Minus infinity. Not many. Maybe you were unable to type in minus infinity. And here on this side, it's 0, 0 to infinity. So those are the correct answers. Okay. That's it. I'll write this down in the notes, but we'll see you guys on Monday. Have a good weekend.